Alright, hello my dudes, we are ready for functions. This is a very exciting day for us. We have a lot to do, and I used the wrong slide layout. That's much better. Let's get started, shall we? So, I think you are probably at the point where you're saying something like, these main functions that we've been writing this entire time, they are huge. If I want to do something, I gotta write int main, and then somehow squish all this stuff inside of main itself, and then return 0, of course, and then closing brace. This could be 1,000 lines for all we know. We need to fix that. Let's break things up. Let's make our own functions. Enough with just main. There is room for more than one person in our program. All right, more than one function. And so here is a misspelling of definition. And also, here is our main function that we know and love now, even including these command line argument parameters. So this is what it takes to make any function, in fact. We've secretly trained ourselves on main itself. So we have a few things that are necessary for any function. There is a return type, int. So that means that this function is going to give back an integer, okay? Return 0, not like hello world. Okay, then there's the function name, of course. That's main. You can give a function any name, just like a variable. It's essentially a variable, in fact. And then you have arguments that you could give to the function. Make it do different things with different arguments. Boop. All those bad boys, argc and argv. And with a custom function, of course, you can make 0 arguments, 1 argument, as many as you want. Give them special names. Of course, they need types as well. Alright, and then you define the function within these braces, just as if it were an if statement or something. You give the body of the entire function, and maybe I can put little dotted lines around that. This is the body. It's in between the braces. Okay? Nothing too horrible. And then optionally, this is not necessary if your function doesn't return anything, but you need a return statement if you need to give back a value. So that one's right here. That's a new keyword for us. Well, we know about it, we just didn't really know what it meant. So this is only necessary if you give back a value. But the fact is, we said main, int main. We gave a promise to the compiler that main will return an integer. And so we better eventually return that integer, give it back to the command line, something like that. So, alright, that's all well and good. We love main. We know main very well. Let's do it ourselves now. Let's write a function to add 2 ints, and then we'll overload it. Okay, so let's think about this. What's our return type? What's our function name? What are our arguments? What should the body be? Are we returning something? Alright, so let's make it be called, I don't know, add. This can be our function's name, and it's going to add 2 ints. So like, it's going to add 42 and 43. And the result of that is going to be another int, right? So it's going to return an int. You see that? That'll be the return type. This will be the name. And we want to be able to call it like this. Just picture a library function as if we were able to say, cout, add 42, 43, just like that. Yeah? That's what we want. Let's make it happen. So that means it's going to take 2 arguments. What are their types? Just like we need to give the types as well as the name. The name doesn't really matter. We can just say x and y and b, whatever. But what are the types of x and y are the question. So what goes here? What kinds of things can we give to our add function? Well, we can give it integers. 2 integers. Int x, int y. And then, suddenly, we can start doing things. Well, the result is immediate, right? We need to give back, through return, the result of adding those 2 numbers. So we'll say return give back x plus y. That's the result. And let me put some space here. Oh man, was that not too bad? Let's do that all over again in code now though. Oh, this should be larger. What do we want to call this? Let's just call it add2. For add two numbers. And our goal is to use this kind of syntax. Cout add 42 and 43. And we just discovered that our add function needs to be called add. It needs to return an integer. It needs to take two things, because we're going to give it two things. Int x, we'll call it an int y. And then, to do the work, we promise that this is going to be an int that we give back, so we better give it back, and return statements give things back. So we'll use that, return, and then the result is x plus y. Please do this, x plus y, and then give it back. Okay? That is, in essence, the idea there. So, this is going to work. So somehow, when we call from main, and I'm going to start drawing a diagram that I will explain later, we start somewhere in main. Don't worry, this diagram, I will explain it in a future lecture. Then we call from main add with 42 and 43. 42 and 42 apparently. Whatever. And then add does its work. That's a 2. And then it gives back its answer to main through that return statement. Give back 84. Okay? That's the idea. This whole process of giving back is returning. Okay? So hopefully that makes sense. We made an add function. It gives back an integer. It's like we replace it with that, with 84. And it takes two things, an int x and an int y, and these don't matter. We could say a or b, as long as we say a and b down here. They're just variables. They will get plopped in, or 42 and 42 will get plopped into these, because that's what we give as arguments to the add function. And so suddenly a inside of here becomes 42. Suddenly b inside of here also becomes 42. Okay? It's like inside the add function, like, hello, here I am in the add function, and I have, well, not x or y anymore, I have a and b, but at least because I'm drawing it here, we'll keep it x and y. X and y, they'll both be 42. Okay, so they have their own variables. Super nice. We can go back to x and y now. So, that's really nice. We just made our first function, guys. We did it. We should clap. One thing that I do want to say immediately is you can have multiple functions with the same name as long as the return types are different. Okay? And the argument types are different as well. Dun dun dun. Actually, no, it's just the argument types. If arg types differ, you can have multiple functions with the same name. So, for example, I can make an add function that works on doubles, an add function that works on strings, and the compiler doesn't care that it's still called add because it has different parameters. So, Whee. Here's one that works on doubles. Here's one that works on strings. I better include string, I guess. But they can all be called add still, is the question, or is the idea. We can make multiple funcs and functions with the same name, as long as the argument types / number of arguments, and/or, I guess, differ. Okay, it just needs to know which one it needs to call. That's all. So we'll hit the int one for that one. We'll hit the double one for this one. And we'll hit the string one for this one. Yeah. And they'll each all do their work of adding things. Because every time we give it values, it just goes and plops in the same position the values that we gave. So 3.14 is what x is. 5.67 is what y is. Now you just return the sum. Okay, so return gives back stuff. And I guess I should say double here and oops, string here. Okay, so let's add. We did it. We made our first function. Now let's write a function to just print hello. Okay, so the body, the entire body is cout hello. Maybe a new line. So, how are we going to do that? And that's an ugly looking cout. Let me fix that. Well, same process. We have hello. Does it need any arguments? No, it just does something. Cout hello and L. So the issue here is, oops, I want these to be on multiple lines for now at least. The issue is, what's the return type? This gives nothing back. It also doesn't need anything to run. So, for example, in main, we just say hello, like that. There's no result needed. It just calling this prints hello. Yeah. So again, it's gonna mess up everything when I save it. Sorry, but what should the type here be? It gives back nothing. It doesn't return anything. What's the type of nothing? And the answer is void. That's what C++ uses. So void is what you use when you don't return anything. Okay? It's a special type, if you will. Special return type, in quotes. Used when you don't return anything. When your function doesn't return anything. Okay. So this will work now, because we will call the hello function with no arguments. And so again, it's like down here in main, we're like, please call the hello function, and then it does it. And hello does its work up here. It does its work, it prints hello onto the screen. There's your keyboard. Prints hello, and then it finishes its work and goes back to main. Okay? Doesn't really return anything at all, but it gives control back to main, I guess. And that's the idea. So main calls hello, hello comes back after it finishes. Okay? So it's as if we replaced all of this with just this, with all these lines in the hello function's body. And I think you can see where we're going with this. We can make main nice and short now. We can split up our tasks into multiple functions that either give back things, don't give back things. It's not an issue. Alright, so now that we know a little bit more about how functions work, now I can talk about function calls again. A function call is just when you use a function to perform some kind of execution, like tell it to go execute its body. That's what a function call means. And so we've already done all of this. You say the function's name, you give it the arguments, the number that it needs, that it requires, and then optionally, you don't always need to, as is the case here. Optionally, if the function gives back something, you can store that, okay, to retrieve it. Retrieve that return value, okay? And now this is going full circle now. If you have parameters in the function definition, that is, dun dun dun, I call them arguments, but secretly they're supposed to be called parameters, now that we know this word. So these are in fact parameters because they're not real values at the moment. So when we write this function, we have an x parameter, a y parameter. Those get filled in with arguments, okay? Parameters in the definition. So if plus a and b, we said in the definition int plus int x, int y, and then we gave our body. These were the parameters, x and y parameters here. And then here, a and b are arguments. Okay? Parameters in the definition receive arguments in the call. If that makes any sense at all. We all get them mixed up, but that's what it should be. Alright? So now we see, we've come full circle. We've seen function calls before, but now we know how to make our own functions and what it means to call a function. Okay? So, the last thing that I want to do is, in this little section, is talk about return versus print. There is a subtle difference, and the question is, how do you use these things in main? Okay? Here are my two functions. I'll attempt to copy them. Return versus print.cpp. Yeah, could be worse. Don't know what that is. Don't know what that is. It appears to have copied correctly. Yeah. Alright, so here in main, how do we use plus? What do we put on both sides? What can we do with plus? How do we use print hello? What do we do on both sides? What can we do? Alright, so that's the question. And I encourage you to take a second to pause, think about what these two functions mean and how you might use them. Alright, now that you're back, let us do this. So, what happens if I call these? Plus 2, 3. Print hello takes no arguments. So, print hello, just parentheses. What happens when I do this? Dun dun dun. Once the plus is ambiguous. There might be a library function that we're shadowing. We will find out. Yeah, So let's call this something other than plus. Let's go back to add. Don't mind me. It's like it never happened. So we'll call it add. And now it should be happy in theory. Oh, did I not save it? Hello? There you go. So I run this program. First it adds, then it prints hello. Huh? What does this mean? What just happened? We only printed hello. Okay. How about I know that add gives back a value, but print hello does not. That means I can use print hello by itself, okay? That's what that means. Add needs to, it's not the full story. There's more to add. Add gives back a value. But it's our job to do something with that value. Okay, so that's the age-old case of returning versus printing. So because add returns, I mean, sure, it gave back 5. We got 5 here. C++ computed 5 and then did nothing with it. Okay? Because it gave it back. It was waiting for us to use it. We can use it by couting it, for example. And now it'll print 5 because we use the return value. We can alter things as well. We can do more. This is going to get replaced with 5. That's what returning means. So we can add 1 as well. Okay? You can just assume that add 2, 3 gets replaced with whatever value it gives back. Okay? Assume each call to add gets replaced with its return value. That's super key right there. Okay? Hello, on the other hand, it gives nothing back. It actually makes 0 sense to do something like this. What? This is calling print hello, but there is no value to replace print hello with. So we'll get a compiler error. It's like something void. Ah, it's trying to use void. There is nothing there. This makes no sense. So print hello just prints. It runs its body, it does something like printing. But add gives back a value. Okay? That's super key. That's what I want to talk about. That's how you use these in main. And it is a mistake, and it is a very common mistake. I'll call this add incorrect. To think that returning is the same as printing. So instead of returning back x plus y, the value, to get replaced with the call, you might be inclined to print x plus y and think that that's the same thing. It is not. Okay? That's extra wrong. This might actually compile. Depends on the compiler. And you might think that it's working as well. Yeah, this is just a warning. It will run. Sorry, return versus print. It prints that 5. And it looked like, and we called the function that gave it x and y. X was 2, y was 3. It printed out 5. But this is incorrect because we're supposed to be able to do this. Do you see that? this won't work properly. This is an error. Or the below. The code below, how about that, is an error. So add incorrect. When we call this, what does it do? It just jumps to its body and it prints out 5. And then it returns some random value because we didn't give anything back. It's going to give back some value, add 1 to that, and then print it. So there's technically 2 coutts happening. The first in the function, the second in the main. Okay? So first it'll call this function print 5, then it gives back some random value, then we add 1 to it, then we print that. See if you can follow along with that. That's important. There we go. So wait for it. Yay. So it printed the 5, then it gave back some random number and added 1 to it, and printed that. So return versus print versus print. I hope that makes sense. We'll give you some more examples of this though. I think that's where I wanted to go with that file. Now let's get at what we're trying to get at here. So the whole reason we're teaching functions, the whole reason people came up with them, is so that you can break down problems into smaller little bite-sized pieces. All right? So here's a sample problem. How can you sum the squares of numbers from 1 to n? So say I give you n, and maybe n is 3. I need you to give me back 1 squared plus 2 squared plus 3 squared. How would you do that? Okay, there is a process involved, and you can usually extract a function from that process. All right? And the fancier word, of course, is algorithm. We know about that word now. It's just a sequence of steps. If we could split up our algorithms, or we could split up our programs into little small algorithms, little small steps, that would be great. All right? That's the goal of this class, really, how to break down big problems into small bite-sized pieces. So we want to make a bunch of little tiny algorithms and just break up functions as much as we can. Like we take our long giant main function from the beginning and we turn that into a bunch of little functions that each do one small specialized thing. And oh man, are those easier to keep track of, easier to work with, easier to prove correct. Oh, it's so beautiful. All right? And this is a fun little GIF. It's a man with a bucket on his head, and then underneath that bucket is another bucket. So that's essentially what we're doing here. We're peeling off the layers of a large algorithm into smaller ones, perhaps. And the whole goal is, I want you to be able to see this kind of problem and write a solution for it. All right? I'm trying to wean you off these step-by-step instructions that I have been giving you, and I probably will give you further into the future. But the goal is to get you thinking on your own, how can you program this? How can you make it work? Okay? Without a bunch of comments with fix-me's on them. All right? And so yeah, that's essentially the process of programming. You will know enough to write very good, well-made programs that can do things. You look at your problem, you figure out what kind of input it needs, and you implement it with as many functions as you need. And you test them, and you debug until it's perfect. You have enough small, tiny functions. And if anything ever goes wrong, a good way to debug, and that just means get rid of bugs in your program, get rid of logic errors, you can use cout and just print the values of your variables, of your parameters, things like that. So that is the goal, all right? And the best way to get there is practice. So here's our problem. What are the pieces? What are the pieces? Take a second to come up with the pieces yourself. What are the pieces of this problem? Right? What are the little steps that you need to do in order to solve the big thing of summing all these squares? Well, here's what I see. We need to sum something. Okay, we need to sum a bunch of squares. So we need to square some things before we sum them. And then we somehow need to enumerate all of these numbers, 1 to n. Okay, those are the 3 things that I see, those 3 steps, those 3 pieces. And then we want to track the flow of data. So which things need to be done before others? First, I need to get these numbers, right? And then I need to square them. And then once I have those squares, I need to sum them. Do you see that? That's the process. That's the order. And so now, because we've noticed this, we can now think about breaking this down. We can think of strategies. We can strategize. This is beautiful. So we can use a for loop to get all these. Yeah? And I can either use star or pow from the math library to get squares. And then I can sum quite easily. I just use the plus. And maybe that can be inside of the for loop as well. Okay? That's our game plan. You see that? It's beautiful. Alright? Functions are so helpful. They will make your life so much easier from now on. Alright? One thing that I do want to encourage you to do is write the barest of minimums at the very beginning. Alright? So write this thing called a stub, and I'll show you what that means. So a stub, that just means a bare minimum piece of code. A bare function. As bare as possible. So, and what I mean by that is it just needs to have a correct definition. The body should be mostly empty. But still compile. And I'll show you exactly what I mean by that. So let's do that for our sum of squares problem. Okay? So let's pretend we get an n from the user, and then we sum the squares from 1 to n. That sounds like a function to me. Sum of squares. .cpp. So, wouldn't it be nice? We could ask the user, hey, enter n. Get it. Output. Sum of squares. N. Yeah? This is beautiful, because now we can start writing programs like this with missing pieces. Okay? We can just assume that we had this function and then go and make it to solve the problem. Do you see how this makes it so much easier to think about things? So now let's make our sum of squares function. What does it take? What does it return? So it's going to take a bunch of integers, or it's going to take an integer n, and it's going to add integers together after squaring them. It'll still return an int, yeah? And then the body will be up to us. We're going to figure that out in a second. But as a stub, this is what a stub means. I just want to get this compiling. I want to get this to work. So I can just return 42. This is a stub. It does the bare minimum. So that the types all work out. But the answer is always wrong. Usually wrong, I guess. It might always be wrong for this problem, but you never know. So we have just made a program, a complete program that compiles. It just doesn't do it right yet, and this is a good starting point. Okay, this is called using stubs. All right, so we just write a bunch of stubs for all the functions that we need to write before getting into the actual code. Okay, that's a stub, and obviously it will just print out 42 every time. Three? Ah, yes, the answer is 42. So this is a great starting point. We can get our program to compile, make sure that there's no other kinds of syntax errors, and then we can work on the actual problem itself. Okay, let's write the real implementation now. Dun, dun, dun. So, remember our breakdown, our game plan? We need to enumerate 1 through n first. We can do that in a for loop. I is less than or equal to n, I plus plus. And then we can go and worry about things. We need to square each number. Each number is I in our case. And then add that square into a sum variable. So we can make like a sum variable up here. We can make a square variable right here. And then we can add into our sum variable square. You see that? What have I forgot to do? What have I forgotten to do, I think? That's the correct past participle. What have I forgotten to do? Well, let's try. Let's try running this. Disregard that. 3. The answer is 4. 5. The answer is 6. 42. The answer is 43. So it appears that it is returning I. Even though I does not exist outside of this for loop, it is returning I to me for no good reason. It's undefined behavior. I'm not giving back a value. I made a promise to return an integer. I must uphold my end of the bargain. Okay? Now to work. 1 squared plus 1, all the way, all the squares from 1 squared to 1 squared, or it's just 1. 1 and 2, that's 1 plus 4, is 5. 3, 14, 42, some large number. And remember what's happening. When I call this function, control of the program stops right here in main. It's waiting. It's waiting for this to finish and give back an answer. It goes straight here. It gives n, which was what the user typed in, maybe it was 3. It puts it in this n. It's a separate n. It's as if, well, it is the case, in fact. Main has an n, and then sum of squares has an n. They are separate places in memory, not the same. And then it's going to call, after we've called this function, we're going to execute its body and give back the answer through the return statement. And that means we can replace this entire function call with the answer, and then we go and print it out. Okay? I hope that makes sense. And with that, we're almost finished. One also nice thing to do is to declare your functions, just like a variable. You can declare a function and define it. Declare a function above main and then define that function below main. Okay? So, here's what we can do. Oop. Yeah, I'm going to I'll copy and paste all of this. And then here's my declaration. Okay? It's just a semicolon with no body. A function without a body is a declaration. Just like this is a declaration of a variable, we can declare a function. Just say, hey C++, this function exists. We'll eventually define it somewhere. Feel free to use it. And then you go and someplace later you can define that function. And this makes it nice and pretty, because main is usually the main attraction of your program, of course. And so it's nice to have main just exist and be the first real function that's implemented. Then you give all the remaining stuff below it. Okay, that's one thing you can do. Alright, and this is still going to work. Some squares, 42, totally works. Obviously, I can't leave out the the declaration, or the definition, at this point it's like, yeah, I know that this function will exist, but I just never got it. It will give, LD stands for the linker, linkage editor. This is a linker error because it was able to compile the program just fine. It made ones and zeros, but then it went looking for all the functions, trying to put them everywhere, link them together, and it couldn't find some squares. All right, so that's beautiful. It's working. It's totally working. The last thing I think I want to show you is we can break this down further, can't we? Dun dun dun. We can square things using a square function, perhaps. How about this? Int square takes a number, x perhaps. We can put it above. And when we square something, what do? We take that thing and give back to it times itself. So return x times x. And now I can replace this with square of x. And it's a bad idea to do this. Same name, it'll shadow things, so I'll say, how about SQ for square? There. Oh, and sorry, this is I. Yeah? You see how we're breaking down problems into even smaller ones? That's beautiful. We just made a square function now. Okay? And it takes one thing, the number that you want squared, and gives back, doesn't print, it gives back that number squared. Alright? So we can do that. And technically we don't need this line, I can just put it right there, but you get the idea. And this will still work. Oops. Beautiful. Alright, so with that, let's get into testing. So, how do you know that your function is correct? Could be your entire program. How do you know that is correct? So, wouldn't it be nice if we could know that our function will always work, no matter what? And, I mean, it's possible. It's possible to check our square function, for example. It takes an int. An int is a 32-bit number. We can enumerate all of them with a for loop. It'll just take a long time. There's 4 billion of them. We can try them all. Make sure that it squares every number properly. At that point, we'd be 100% confident. We can just write a 4 billion line program with an if statement on each line, something like that. Of course, this is not feasible for everything. And the second you start having strings, for example, with arbitrary length, arbitrary characters, you cannot enumerate every possible thing that you can give into that string variable. All right, so it is possible to prove functions correct. That's more of a graduate topic, but testing is something we can do right now. And we'll write these things called unit tests to test small little pieces. Okay, that's what unit testing means. We pick a unit of our program, a small chunk, usually it's a function, and we write a bunch of test cases, we say, for that little chunk, for that unit. Okay, so I think I'd rather write a simpler kind of thing to test things with. So how about, let's make our factorial function. All right. Let's make this factorial function, and then we're going to test it. Factorial.cpp. All right, so we need to write a factorial function. Remember what it does. It's like, all right, 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. So a factorial of an integer, it takes an integer. There is a parameter, isn't there? We're going to be able to call it like this. Factorial, and we'll call it fact of 3. Yeah? There are parameters, there's 1. And because we want this to give back a value, the return type should not be void. It should be int. Okay, there's 1. It's an int. What should the name of this function be? Well, we'll call it fact, perhaps. And then let's go and write our stub. And then we'll test that stub. This is called test-driven development, by the way. We're developing tests with our program. So int fact, int x, declaration, definition, return 42. Now it's a stub. It's incorrect, of course. How do we check that it's incorrect? We can write many a test case. So a test case is just a Boolean expression, something that returns true or false, that compares what you expect with what you got. Okay? So for example, fact of 1 should be equal to, when it returns, 1. Okay? And we can test that with an if statement. And if it's not true, it's not equal to 1, then we say fact is wrong. You see where I'm going with this? I can do the same for more inputs until I'm reasonably confident that the factorial function is fine. This is 2, this is 3, 2 should be 2, 3 should be 6, yeah? And this can be our program. We made a fact function. It's not correct yet, obviously, it's just a stub. And then we can make a bunch of tests that would help convince us that our factorial function is correct. Okay? So we compare what we expect with what we got, and we want to be thorough. We don't want to test just a few things. We want our test to cover the code in question, and I'll talk about that in a second. And we want to try every different kind of input that we could possibly give to hit every place in our program. But right now, let me just show you the test cases running and working. No, sorry, it's factorial now. /factorial. So it's incorrect, obviously. We can make it correct sometimes and still have an incorrect function. You see that? You see that? You see why it's important to have multiple tests? Fact 1 is correct, but the other ones catch the problem. All right, so let's actually go and implement this properly. So our factorial function, it's going to, for example, factorial of 3 is going to need to multiply 3 times 2 times 1. And so I hope you can see a nice for loop here, or just any kind of loop. As long as you're greater than 1, just keep on multiplying yourself somewhere. So we can have int product starting out at 1, and then just keep on counting down from x to x minus 1 to x minus 2, all the way to 1, until we get there. Then we'll return that product. All right? So here's the idea. For int I equals x, I is greater than or equal to 1, I minus minus. So if x was, for example, 3, then we would do this. X would be 3, then 2, then 1, and stop. So we'll say product equals product times x, or sorry, times I, and then we'll return the product. Okay, and I hope you see that this is going to work, assuming I didn't make any silly mistakes, because product will start out at 1, and then I will range between 3 to 2 to 1. Starts at 3. Then we multiply 3 into I, or into product. So now it's 3. Now we subtract 1 from I, now it's 2. Now this is 6. Now we get to 1, and then we multiply it by 1, still 6. And then we stop the loop. Okay? So then product will be 6, so we can return that. And this is a correct function. Or is it? Well, it just so happens that all of our test cases pass. We get no output anymore. But we want to cover the code. That means make sure every nook and cranny has been reached by a test. Okay? We want to reach everywhere with a test. Oops, out. Everywhere in the code. Did we try every kind of input? Stare at this for a second, did we? What about fact of -1? Well, it's 1. That's not correct. Shouldn't even be defined, right? So there is the problem. We need more tests. We need to say like fact minus 1. Maybe we can always give -1 for an incorrect factorial, for example. But we need to pick a problem. We need to cover our code. And we can say if x is less than 0, return -1 immediately. Okay? And I guess I do want to show you this now. You don't have to use braces for a single line if statement. If the body's just one line, this will trip you up though. I encourage you to use braces for the rest of your life, or as long as you can remember to do this. Okay? So that's the idea. Maybe now I'll return -1 if I ever get a weird value for my factorial function. And so now again I have working tests. I think I cover the code pretty reasonably with these 4 tests. I hit every line. I hit this line, the if statement returning the -1. I hit these ones. You can return multiple places in your function, of course. And then I cover the non-negative case. And if it's 0, the factorial is defined to be 1, so it'll still work. That's the idea. We have just tested this function. It's all so beautiful. Let me see how we're doing. I think this is where I want to stop us. We'll come back with these. Actually, no, I think let's just do these. Let's finish them. They're very quick. So what's wrong with this function? Maybe pause the video and see if you can figure it out. It's supposed to square things. We've made a square function now. What's the problem? And I think you might see that the types are a bit interesting this time. X is a double. So let's see here. That's interesting. Oh wait, that's not even the problem though, is it? Because when I run this program, I give it x. Let's just walk through it. 3.14. I calculate squared number. It's x times x. Made to be an integer, which might be an issue. So it's 9. It's going to be set to 9. It's going to drop all the decimal places. And then it's going to return x. Oh, it's returning 3.14. Oh, shoot. It shouldn't return. Actually, it should return squared number. But squared number is still incorrect. So what's a test case that might exhibit this problem? 3.14. Something that I know of, like if square of, I don't know, 2.5 is unequal to, what's 2.5 squared? Is that? I don't immediately remember. You're going to laugh at me. It's been too long. 6.25 apparently. If it's not that, then see out error. Okay? So that's a good test case. That'll catch this, because obviously it'll give back 2.5 in this case. Alright, how about this one? Take a second. This one has the other problem. It still has all this. Oops. This time it gives back squared number, but squared number is the wrong type. You see that? So, again, the exact same test case will cover it. Or you could write others, just as long as the squared number is not a whole number, because this test will pass. Square of, I don't know, square of 3.0 is in fact 9.0. That will work. You can even use double equality for that. That's the idea. Okay? So this is how you can test things, make sure that it's doing the right thing. If you write enough test cases, it'll all work out. Okay? So that is where I want to leave you, and we'll come back with this beautiful thing called the stack in the next lecture.